And in this video we will be proving that the sum of any twin primes that are greater than 3 and 5 will always be divisible by 12. So we can write it like this, that 12 will divide p plus 2 for p greater than 3. This ensures that our set of primes is greater than 3 and 5. So in order to prove this, I'm going to express this prime p in terms of an arbitrary integer k and another arbitrary integer r, where k will be an element of the natural numbers and also greater than 0, and r will be an integer that can take on the values -1, 0, 1, 2, 3, and 4. The reason why I have this set of numbers is because if we take p mod 6, then this is equal to r. Therefore, r can only take on the values that I have listed right here. And the reason why I don't include 5 is because 5 is equivalent to -1. And the reason why I don't include 6 is because 0 is equivalent to 6 mod 6. And if we consider the case that r is equal to 4, then we can express p as 6k plus 4. But right away we see that we can factor out a 2 and get this expression, which suggests that this prime number is divisible by 2. Therefore, that is a contradiction. And that means that r cannot equal 4. So we know that we can't express a prime number when r is 4. So I'm going to cross that off the list. So now let's check the case where r is equal to 3. And if r is equal to 3, we express the prime p as 6k plus 3, or we can now factor out a 3. And this suggests that this prime number is divisible by 3, but that contradicts with the definition of a prime, and we eliminate 3 from the list. So let's continue this. We now have the case that r is equal to 2. So we express the prime number as 6k plus 2, where we can see that we factor out a 2, we get 3k plus 1. This leads to a contradiction because it suggests that this prime is divisible by 2. Therefore, we can eliminate the case when r is equal to 2. So how about the case where r is equal to 1? So we can write it as p is equal to 6k plus 1. And right here I don't see any immediate contradiction. So I'm going to come back to this case right here. Now let's check when r is equal to 0. So we have p is equal to 6k, where this suggests that 6 divides p, which is a contradiction to the idea of a prime. So we can eliminate that case. And now let's check our last case, whenever r is equal to -1. So we can express p as 6k minus 1 for k greater than or equal to 1. And just like this case, we see that there's no immediate contradiction. So we can say that the only possible forms that p can take on are the forms 6k minus 1 or 6k plus 1 for k greater than 0. So these represent the forms that the twin primes can take on. So if we have p, it'll be 6k minus 1, and then if we have p plus 2, it'll be 6k minus 1 plus 2, which is equal 12k. And by definition of division, we can reason that 12 divides 12k. Therefore, 12 divides p plus 2, which is what we sought out to prove, and therefore the proof is done.